There is a moment, frozen in the mathematics of the universe, where time itself fractures. Not breaks, fractures. Like ice under weight, it splinters into parallel streams, each flowing at its own pace, each indifferent to the other. This moment arrives not through magic or divine intervention, but through speed. Simple, brutal, relativistic speed. Imagine an astronaut. She is 25 years old. Her daughter is 5. They embrace at the base of a spacecraft designed to touch the edges of light speed, to graze the cosmic speed limit that governs all matter, all energy, all possible motion in this universe. The mission duration, as measured by the clocks on board the vessel, is 10 years. 5 years out, 5 years back. The astronaut will age 10 years. She will return 35 years old, perhaps with grey hairs beginning to thread through the dark, perhaps with a particular weariness that comes from a decade of isolation among the stars. But her daughter will not be 15 when she returns. Her daughter will be 55. A grandmother, perhaps. A woman who has lived an entire life, loves, losses, marriages, careers, the slow accumulation of joys and sorrows that constitute a human existence while her mother was away. The astronaut will return to find her child older than she is. She will attend a funeral for parents who died of old age while she was still young. She will meet grandchildren who never knew her, who know her only as a ghost, a myth, the woman who went to the stars and came back wrong, came back unstuck in time. This is not science fiction. This is science fact. This is the price written into the fabric of reality itself, encoded in equations that have been tested, verified, measured to absurd precision. Einstein discovered this price in 1905, and we have been paying it ever since. Every GPS satellite, every particle accelerator, every cosmic ray that strikes our atmosphere, they all pay this price, they all bend to this law. Time is not universal. Time is not absolute. Time is not fair. And if we wish to travel among the stars, if we wish to spread across this galaxy in our fragile vessels of metal and hope, we must sign a contract with the cosmos itself. The contract is simple. You may approach the speed of light, but you will leave everything you love behind, not in space, but in time. You will become an exile not from your homeland, but from your era. You will return to a world that has moved on without you, that has forgotten you, that has buried you in history books while you still draw breath. This is the tragedy of relativistic time dilation. This is the price of speed. Before Einstein, before the equations that would shatter our understanding of reality, there was a comfortable lie. The lie was this: time flows the same for everyone, everywhere, always. A second on Earth is a second on Mars, is a second in the furthest reaches of intergalactic space. The universe, we believed, marched to a single drumbeat, a cosmic metronome ticking away with perfect regularity. This was the Newtonian dream, a clockwork universe where cause and effect unfolded in perfect synchronization, where simultaneity was absolute, where time was the stage upon which the play of existence unfolded, unchanging and eternal. Newton himself wrote of this in his Principia: absolute, true, and mathematical time, of itself, and from its own nature, flows equably without relation to anything external. Time, in Newton's conception, was a river that flowed at the same rate for all observers, regardless of their motion, regardless of their position, regardless of anything they might do. You could not speed it up. You could not slow it down. You could only float upon its surface, carried inexorably from past to future at the same rate as every other conscious being in creation. This was beautiful. This was intuitive. This was wrong. The crack in Newton's perfect clock appeared slowly, over decades, through accumulated observations that refused to fit the model. Light, it turned out, behaved strangely. In the late 19th century, physicists noticed something disturbing. The speed of light seemed to be constant regardless of the motion of the source or the observer. If you were standing still and measured the speed of a light beam, you got a certain number, approximately 300,000 kilometers per second. If you were moving toward the light source at half the speed of light, Newtonian physics said you should measure the light approaching you at 450,000 kilometers per second. But you didn't. You measured 300,000 kilometers per second. Always. Without exception. This made no sense. It violated every intuition about how motion should work. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone standing beside the tracks sees the ball moving at 120 kilometers per hour. Velocities add. This is obvious. This is foundational. Except with light, velocities don't add. Light moves at the same speed for all observers, regardless of their motion. The universe seemed to be playing a cruel joke, presenting us with a phenomenon that refused to obey the rules we had spent centuries establishing. In 1905, a 26-year-old patent clerk in Bern, Switzerland, solved the puzzle. Albert Einstein, working in his spare time while evaluating patent applications for electromagnetic devices, published a paper with the modest title on the electrodynamics of moving bodies. The paper was 17 pages long. It contained no citations. It referenced no experimental data. It was pure thought, pure logic, the product of years of mental experimentation, of imagining what it would be like to ride alongside a beam of light. Einstein's insight was radical in its simplicity. What if the constancy of the speed of light wasn't the problem? What if our assumptions about space and time were the problem? What if, instead of space and time being absolute and unchanging, they were flexible, malleable, dependent on the observer's motion? What if time itself could slow down or speed up? What if distances could contract or expand? What if the universe achieved the constancy of light speed by warping the very fabric of reality? The mathematics that fell out of this insight were elegant and terrible. Einstein showed that time is not absolute. For an observer moving at high velocity relative to a stationary observer, time passes more slowly. Not subjectively, this isn't about perception or psychology. Objectively, measurably, time itself runs at a different rate. The moving observer's clock ticks slower. Their heartbeat is slower. The decay of radioactive atoms is slower. Every process, every phenomenon, every tick of existence unfolds at a reduced pace. How much slower? The factor is given by what we now call the Lorentz factor, named after Hendrik Lorentz, who had derived the mathematical transformation before Einstein but hadn't understood its physical meaning. The equation is deceptively simple. Gamma equals 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. In symbols, gamma equals 1 square root 1 v squared c squared. At everyday speeds, this factor is essentially 1. At 100 km per hour, freeway speeds, the Lorentz factor is 1.000000000000000388. The difference is 17 decimal places deep, utterly negligible, completely undetectable. This is why Newton's absolute time worked so well for so long. At human speeds, at the speeds of cannonballs and trains and even supersonic jets, relativity is invisible. Time dilation exists, but it's buried beneath layers of decimal points, a ghost effect that makes no practical difference. But as velocity increases, as you begin to approach a significant fraction of the speed of light, the Lorentz factor grows. At 10% of light speed, gamma is 1.005. Time passes 0.5% slower. Still small, but detectable with precise instruments. At 50% of light speed, gamma is 1.155. Time passes 15.5% slower. Now we're in the realm of serious divergence. At 90% of light speed, gamma is 2.294. Time passes less than half as fast. For every 2 years that pass on Earth, less than 1 year passes aboard your spacecraft. And as you approach light speed asymptotically, as v gets closer and closer to c, the Lorentz factor explodes toward infinity. At 99% of light speed, gamma is 7.089. At 99.9%, it's 22.366. At 99.99%, it's 70.712. The curve is exponential, merciless. At 99.999999% of light speed, 8 nines, the Lorentz factor exceeds 2236. You could travel for what feels like 1 year and return to find 5,000 years have passed on Earth. Civilizations would have risen and fallen. Languages would have evolved beyond recognition. The continents themselves would have shifted beneath different skies. This is the unchanging clock, the cosmic law that cannot be circumvented, cannot be negotiated with, cannot be wished away. Einstein didn't invent time dilation. He discovered it, uncovered it like an archaeologist brushing dust from ancient stone. The law was always there, written into the mathematics of spacetime, waiting for creatures clever enough to decipher its terms. And the terms are clear: if you wish to travel fast, you will pay with time. Not your time, that's the cruelest twist. You will pay with everyone else's time. You will steal decades, centuries, millennia from those you leave behind. They will age. They will wither. They will die. And you will remain young, preserved in the amber of relativistic velocity, a time traveler not by choice but by physics, moving forever forward into a future that grows increasingly alien, increasingly incomprehensible, increasingly alone. The clock is unchanging in its indifference. It ticks for everyone, but not at the same rate. And once you understand this, once you truly internalize what it means, space travel transforms from adventure into something darker. Something more like sacrifice. Something more like suicide in slow motion, where you die not to injury or old age, but to relevance, to connection, to the shared timeline of your species. This is what Einstein gave us, not just a new understanding of the universe, but a new kind of tragedy. A tragedy written in mathematics, proven by experiment, and inescapable as gravity itself. The speed of light is not merely a speed. It is a barrier, a cosmic wall separating the possible from the impossible, the real from the forbidden. 300 million meters per second. 1 billion kilometers per hour. Fast enough to circle the Earth's equator 7.5 times in a single second. Fast enough that if you could somehow achieve it, you could reach the Moon in just over a second, reach Mars in minutes, reach the nearest stars in years. And yet, fundamentally, insurmountably, impossibly too slow. Consider what the speed of light actually means for cosmic travel. Our nearest stellar neighbor, Proxima Centauri, lies 4.24 light-years distant. This means that light itself, the fastest thing we know, the universal speed limit, takes 4.24 years to make the journey. Not years as measured by a traveler approaching light speed, but absolute distance divided by absolute velocity. The gap is so vast that even moving at the fastest possible speed, the universe imposes a minimum travel time measured in years. But Proxima Centauri is cosmically adjacent, a next-door neighbor in galactic terms. The Milky Way galaxy spans 100,000 light-years. The Andromeda galaxy, our nearest galactic neighbor, lies 2.5 million light-years away. The observable universe extends 46 billion light-years in every direction. Even at light speed, even moving as fast as causality itself permits, crossing these distances requires timeframes that dwarf human lifespans, that exceed the entire recorded history of human civilization, that approach the lifetime of stars themselves. The speed of light is fast. The universe is vastly, incomprehensibly, grotesquely larger. Einstein's relativity tells us something even more devastating than the mere numerical value of light speed. It tells us that light speed is not just the current record holder, not just the fastest thing we've discovered so far, but the absolute limit written into the laws of physics themselves. Nothing with mass can reach light speed. Not with better engines, not with more fuel, not with any amount of energy. The prohibition is mathematical, fundamental, unbreakable. Here is why, as an object with mass accelerates, it becomes harder and harder to accelerate further. In Newtonian physics, if you apply a constant force to an object, it accelerates at a constant rate forever. Double the time you apply the force, double the final velocity. Simple, linear, unlimited. But relativity introduces a correction factor, that same Lorentz factor we encountered before. As velocity increases, the effective mass of the object increases by the Lorentz factor. The object becomes harder to push, as if it's growing heavier even though its rest mass hasn't changed. At 90% of light speed, the effective mass is more than double the rest mass. At 99%, it's more than 7 times the rest mass. At 99.9%, more than 22 times. As velocity approaches light speed, the Lorentz factor approaches infinity. The effective mass approaches infinity. The energy required to accelerate further approaches infinity. You would need infinite energy to reach light speed. And infinity is not available. Infinity is not a large number. Infinity is not a number at all. It is a statement that something is impossible. This is the prison of light. We are trapped behind bars made of mathematics, locked in a region of velocity space that extends from 0 up to, but never including, 299,792,458 meters per second. Every massive object in the universe shares this prison. Every atom, every photon with mass, if such things existed, every spacecraft we will ever build, all confined to the subliminal realm, all forever barred from reaching the one speed that would make the universe navigable. Why did the universe impose this limit? The question is almost theological. Physics doesn't answer why in the teleological sense, it simply describes what is. But we can explore the implications. If light speed weren't a limit, if velocity were truly unlimited as Newton believed, then causality itself would break down. Events could occur before their causes. Information could travel backward in time. The sequence of cause and effect that gives structure to reality would dissolve into paradox and inconsistency. The speed of light limit is, in some sense, the universe protecting itself from logical contradiction, from the chaos that would ensue if effects could precede causes. Light itself, of course, travels at light speed. Photons are the only particles we know that move at exactly c, always and without exception. But photons are massless. They pay a different price for their velocity. From a photon's perspective, if we can speak of such a thing, time does not pass at all. The Lorentz factor at light speed is infinite, meaning time dilation is infinite. A photon emitted from a distant quasar billions of years ago, from the perspective of the photon itself, arrives at your eye in the same instant it was emitted. For the photon, there is no journey, no duration, no experience of time. It exists in an eternal now, launched and arriving simultaneously. This is the trade-off the universe offers. You can have mass and experience time, but you must move slower than light. Or you can move at light speed, but you must have no mass and experience no time. You cannot have both. The universe does not permit it. We discovered this prison slowly, painfully, through experiments that challenged our intuitions. The Michelson-Morley experiment of 1887 was the first major crack in the Newtonian edifice. Physicists expected to measure Earth's motion through the luminiferous ether, the hypothetical medium through which light was thought to propagate as sound propagates through air. They built an interferometer of exquisite sensitivity, capable of detecting tiny differences in the speed of light in different directions as Earth moved through the ether. The experiment was beautifully designed, meticulously executed, and completely baffling in its results. There was no difference. No matter which direction they measured, no matter the time of day or year, light moved at the same speed. The ether, if it existed, was undetectable. Or perhaps it didn't exist at all. This result haunted physicists for nearly 2 decades. Various explanations were proposed, increasingly baroque and unsatisfying. Lorentz and Fitzgerald independently suggested that objects contract in the direction of motion by just the right amount to cancel out any ether effect, a proposal that was mathematically correct but physically unexplained. It took Einstein to cut through the confusion with a razor. The ether doesn't exist. Light doesn't need a medium. It propagates through the vacuum itself, and it always moves at the same speed relative to any observer. The constancy of light speed is not a puzzle to be solved. It is a fundamental postulate of nature. Once you accept this postulate, once you take it as given that light speed is constant and finite, everything else follows. Time dilation follows. Length contraction follows. The relativity of simultaneity follows. The speed limit follows. Einstein showed that the Michelson-Morley result wasn't a mysterious cancellation of effects. It was the universe showing its true face, revealing that space and time are not the fixed stage we imagined but dynamic, interconnected aspects of a four-dimensional space-time continuum. The prison of light is not a cage imposed by human limitations or technological inadequacy. It is deeper than that. It is a feature of the universe itself, as fundamental as the existence of space, as unavoidable as the arrow of time. And it means that when we look up at the night sky, when we see stars and galaxies scattered across incomprehensible distances, we are looking at a map of our isolation. Each point of light represents a destination that, even at our fastest possible speed, would take years or centuries or millennia to reach. The universe is vast and we are slow, and no amount of engineering or ingenuity can change this fundamental asymmetry. Unless we find a loophole. Unless we discover that Einstein's relativity, for all its experimental confirmation and mathematical elegance, is not the final word. Unless there are ways to traverse space that don't require moving through it at subliminal speeds, wormholes, warp drives, higher dimensions, exotic physics we haven't yet imagined. These possibilities exist in equations, in speculative papers, in the mathematical playground where theoretical physicists explore the consequences of general relativity pushed to its extremes. But they remain speculation. What we know for certain, what has been measured and verified countless times, is the prison. We know the walls are real. We know the bars are unbreakable. We know that light speed is not just a current technological limitation but a fundamental feature of reality, and that any journey we undertake among the stars will be constrained by this limit, will be shaped by this barrier, will exact the price that time dilation demands. The speed of light is our prison, and the sentence is eternity. Imagine space-time as a fabric. This is more than metaphor. It is how physicists actually conceive of the universe at the deepest level. Not empty void with objects moving through it, but a four-dimensional continuum where space and time are interwoven threads, inseparable and interdependent. When you move through space, you also move through time. When gravity bends your path through space, it simultaneously bends your path through time. The fabric is real, in the sense that it has structure, curvature, dynamics. It can ripple with gravitational waves. It can be stretched by the expansion of the universe. And crucially, for our purposes, it can be torn. Not literally torn. Space-time doesn't rip like cloth. But it can be deformed, stretched, distorted in ways that separate observers into different temporal realities. This is what velocity does. This is the mechanism behind time dilation. When you accelerate to relativistic speeds, you don't just move faster through space. You tilt your trajectory through space-time, you rotate your world line, you alter the ratio between your motion through space and your motion through time. And in doing so, you separate yourself from the shared temporal reference frame of the stationary universe. You create a bubble of slower time around yourself, a protected region where seconds tick more slowly, where aging proceeds at a reduced rate, where the future arrives less quickly. The mathematics of this distortion are encoded in the metric tensor, a mathematical object that describes the geometry of space-time. In flat spacetime, no gravity, no acceleration, the metric is simple, diagonal, unchanging. But introduce motion, introduce acceleration, introduce mass, and the metric warps. The components mix. Space and time become coupled. Your trajectory through one affects your trajectory through the other. Let us be concrete. Suppose you are at rest on Earth. Your world line, your path through four-dimensional spacetime, points directly forward in time. Every second, you advance 1 second into the future. You move through time at the maximum rate, at 1 second per second, because you are not moving through space at all, ignoring Earth's rotation and orbit, which introduce tiny relativistic effects we'll disregard for now. All your motion through spacetime is temporal motion. You are stationary in space, maximal in time. Now suppose you accelerate. You build velocity. You begin moving through space. Your world line tilts. The four-dimensional vector that represents your motion through spacetime now has a spatial component. And here is the crucial insight. The length of your world line, your proper time, the time you experience, is constrained. In the language of spacetime geometry, your velocity has a fixed magnitude. You are always moving through spacetime at light speed. Always. Without exception. Every object in the universe moves through spacetime at exactly the speed of light. This sounds paradoxical. How can everything move at light speed when we know that massive objects cannot reach light speed? The resolution is that we're talking about motion through spacetime, not motion through space alone. Your velocity has both temporal and spatial components. When you're at rest spatially, all your velocity is directed through time. You're moving through time at light speed, advancing 1 second into the future for every second of proper time. But when you start moving through space, some of your velocity gets redirected. You trade temporal motion for spatial motion. You move faster through space, but slower through time. The total magnitude remains constant. You're still moving through spacetime at light speed, but the distribution changes. This is why time dilation occurs. This is why moving clocks run slow. When you move through space, you have less velocity budget left over for moving through time. Your seconds stretch out. Your heartbeat slows, relatively speaking. The universe outside your reference frame ages faster than you do, not because something magical is happening to you, but because you've tilted your world line, redirected your motion through spacetime, traded your temporal velocity for spatial velocity. The Lorentz factor, that gamma term we keep encountering, is simply the mathematical expression of how much your world line has tilted. At low velocities, the tilt is negligible. At high velocities, the tilt becomes severe. At light speed, if you could reach it, your world line would be tilted completely horizontal in a spacetime diagram. You would be moving entirely through space with no motion through time at all. You would be frozen in the eternal now that photons inhabit, experiencing no duration, no aging, no passage of time whatsoever. But you cannot reach light speed. Your world line cannot tilt completely horizontal. The Lorentz factor prevents it, growing without bound as you approach that limit, requiring infinite energy to close the final gap. So you are confined to world lines that are mostly temporal with varying degrees of spatial tilt. And that tilt, that rotation of your path through spacetime, is what separates you temporally from those who remain at rest. Consider the geometry more carefully. In flat spacetime, simultaneity is well defined. Events that are simultaneous for one observer are simultaneous for all observers at rest relative to that observer. Draw a spacetime diagram, time vertical, space horizontal. Pick a point representing now for a stationary observer. The set of all events simultaneous with that point forms a horizontal line, a plane of simultaneity extending infinitely in both spatial directions. Every event on that line happens at the same time for the stationary observer. But now introduce a moving observer. Their world line is tilted. Their conception of now is different. The plane of simultaneity for the moving observer is not horizontal. It's tilted at an angle determined by their velocity. Events that the stationary observer considers simultaneous are not simultaneous for the moving observer. Events that are in the future for the stationary observer might be in the present for the moving observer. Events in the past for one might be present for the other. Simultaneity is relative. Now is relative. There is no universal present moment that all observers agree upon. This is not a perceptual effect. It is not about signal delays or the time it takes light to travel. It is about the fundamental structure of spacetime. Two observers in relative motion genuinely, objectively disagree about which events are happening right now at distant locations. They inhabit different temporal slices of the same spacetime. They are separated not just by distance but by divergent definitions of simultaneity itself. This leads to what are called the relativity of simultaneity effects, and they can be profoundly strange. Suppose you are on Earth and your friend is on a spacecraft traveling away from Earth at 90% of light speed. You watch a supernova explode in a distant galaxy and call it now. But from your friend's perspective, moving away from that galaxy, the supernova is still in the future. It hasn't happened yet. Your now is there soon. If they were to turn around and travel back toward the galaxy at the same speed, suddenly their plane of simultaneity tilts the other way, and the supernova is now in their past. It already happened. Your now is there ago. The supernova itself doesn't care. It explodes when it explodes, sending light propagating outward at light speed in all directions. The objective event is fixed in spacetime. But when it happens, what time it occurs, depends on your state of motion. And this dependence is not illusory. Both perspectives are equally valid. There is no privileged reference frame, no God's eye view that declares one observer correct and the other mistaken. The universe does not come with a master clock. This is the fabric tearing. Not physical rupture but conceptual divergence, observers peeling away from each other into separate temporal realities, each equally valid, each seeing the universe age at different rates, each inhabiting a different now that slides across spacetime at angles determined by velocity. And when one of those observers is traveling at extreme relativistic speeds, the divergence becomes catastrophic. The traveler's time slows to a crawl relative to the stationary observer. The stationary observer's time races ahead from the traveler's perspective. They are both moving through spacetime at light speed, but their world lines have tilted so far apart that the temporal distance between them grows vast, unbridgeable. And when the traveler returns, when they decelerate and tilt their world line back toward the vertical, they find that their now has slid centuries into the future. The fabric didn't tear. It stretched, distorted, allowed them to take a shortcut through time while everyone else took the long route. The traveler experienced less proper time, fewer seconds ticked by on their clock, fewer heartbeats, fewer breaths. But the universe outside did not slow down for them. It continued apace, indifferent, aging normally in all the reference frames that didn't accelerate to relativistic speeds. This is the mechanism. This is how time dilation works at the geometric level. Your world line is your path through spacetime. When you move, you tilt that path. When you tilt that path, you redistribute your motion between space and time. When you redistribute your motion, you age more slowly relative to those at rest. The effect is not psychological, not technological, not subject to human will or ingenuity. It is geometric. It is built into the structure of spacetime itself. Einstein called it the invariant interval, the spacetime distance along your world line, the proper time you experience. That interval is what it is. Physics guarantees its invariance. And if your world line takes a tilted path through spacetime while others take a vertical path, you will experience less proper time. You will age less. You will arrive in the future having lived fewer years than those who stayed home. The fabric does not tear. But it might as well. The effect, for those separated by relativistic velocities, is functionally indistinguishable from a rupture. They diverge. They drift apart not in space but in time. And when they reunite, if they ever reunite, they find themselves strangers, separated by decades or centuries of subjective time, meeting across a chasm that velocity carved into the smooth continuum of spacetime. This is the price. This is the mechanism. This is why traveling fast means traveling alone. Chapter 4. The twin paradox, a thought experiment in Mourning. There are two sisters. Let us call them Anna and Clara. They are twins, born minutes apart, identical in every measurable way, same genes, same upbringing, same education, same dreams of seeing the stars. On their 25th birthday, they stand together at the launch facility, embracing one final time before Anna boards the spacecraft. The mission is clear: travel to a star system 12 light-years distant at 80% of the speed of light, establish observational data, then return home. The journey, as measured by Anna's onboard clock, will take 20 years. 10 years to reach the destination, 10 years to return. She will age 20 years. She will return to Earth at age 45. Clara waves as the spacecraft departs, watches it accelerate away, watches it vanish into the black. Then she goes home. She continues her life, her work, her relationships, the ordinary accumulation of days that constitutes a human existence. She thinks of her sister often, imagines her in that vessel, crossing the vast distances between stars. She counts the years as they pass. Anna, aboard the ship, experiences the journey as planned. The stars ahead blue shift as her velocity carries her toward them. The stars behind redshift, their light stretched by the Doppler effect. Time, from her perspective, flows normally. She eats meals, sleeps, maintains the ship systems, conducts her research. Her heart beats at its usual rhythm. Her cells divide at their usual rate. 20 years pass, subjectively. She reaches the target star system, gathers her data, turns around, and begins the return journey. Another 10 years pass. She approaches Earth. She prepares to land. She is 45 years old. She has aged exactly as much as she expected. But when she lands, when she opens the hatch and steps out onto the landing pad, Clara is not there to greet her. Clara is 75 years old. Clara is an old woman, grey-haired and frail, supported by grandchildren who help her walk. 50 years have passed on Earth. 50 revolutions around the sun, 50 winters and springs and summers and autumns. Half a century. An entire human lifetime compressed into the subjective experience of 20 years aboard a relativistic spacecraft. Anna is 45. Her sister is 75. They are no longer twins in any meaningful sense. They have diverged by 3 decades of life experience, 3 decades of aging, 3 decades of time that pass for one but not the other. Anna has lost 30 years of her sister's life. She was not there for Clara's wedding. She was not there when Clara's children were born. She was not there when their parents died. She missed the entire middle act of Clara's life, and that time is gone, irretrievable, lost to the relativistic void. This is the twin paradox. Not truly a paradox, the mathematics are clear and consistent, but a scenario that violates every intuition we have about time, about aging, about the symmetry of sibling bonds. The setup seems paradoxical because, from Anna's perspective, it is Clara who moved away. After all, motion is relative. Anna could argue that she remained stationary while Earth and Clara receded at 80% light speed, then approached at 80% light speed on the return. If motion is truly relative, shouldn't the time dilation be symmetric? Shouldn't Clara also have aged more slowly, resulting in both twins being 45 upon reunion? But the situation is not symmetric. And here is why: Anna accelerated. Clara did not. Anna's reference frame changed. Clara's did not. Acceleration breaks the symmetry. Special relativity, strictly speaking, deals only with inertial reference frames, frames moving at constant velocity relative to each other. But Anna's journey required acceleration. She had to speed up to 80% light speed, then decelerate at the turnaround point, then accelerate again for the return, then decelerate upon arrival at Earth. Each of those accelerations changed her reference frame, rotated her plane of simultaneity, introduced asymmetry into the scenario. During the turnaround, the moment when Anna decelerates, stops, and accelerates in the opposite direction, her plane of simultaneity sweeps across space-time. From her perspective, Earth's clock suddenly jumps forward. In the instant of her turnaround, decades pass on Earth. This is not because time on Earth actually speeds up. It is because Anna's definition of now shifts dramatically. Before the turnaround, distant simultaneous events on Earth were relatively recent. After the turnaround, distant simultaneous events on Earth are much further in the future. The turnaround itself is the asymmetry. It is the reason Anna ages less than Clara, the reason the mathematics unambiguously predict that Anna returns younger. Let us examine the numbers more carefully, because the twin paradox is not just qualitatively strange but quantitatively devastating. Anna travels 12 light-years at 80% of light speed. In Earth's reference frame, the journey takes 15 years each way, 12 light-years divided by 0.8 c. Round trip, 30 years. But we must account for acceleration and deceleration. Let us assume negligibly short acceleration periods for simplicity, though in reality these would take months or years at tolerable g-forces. In Earth's frame, Anna's journey takes slightly more than 30 years, including turnaround time. Let us call it 32 years total, accounting for realistic mission parameters. But Anna does not experience 32 years. The Lorentz factor at 80% light speed is 1.667. Time dilation means Anna's clock runs slower by this factor. For every 1.667 seconds that pass on Earth, 1 second passes on Anna's ship. Over the course of the journey, Anna experiences 32 divided by 1.667, which equals approximately 19.2 years. Call it 20 years for a round number, including all mission phases. So Clara ages 32 years. Anna ages 20 years. The difference is 12 years. If they were both 25 at departure, Clara is 57 and Anna is 45 upon reunion. Still significant, still painful, but perhaps tolerable. They are both middle-aged. They can still relate to each other. The gap is not insurmountable. But now increase the velocity. Suppose the spacecraft can reach 95% of light speed. The Lorentz factor is now 3.203. Anna experiences 32 divided by 3.203, which equals approximately 10 years of subjective time. She ages 10 years. Clara ages 32 years. Anna is 35. Clara is 57. The gap has doubled. At 99% of light speed, the Lorentz factor is 7.089. Anna experiences 4.5 years. Clara experiences 32 years. Anna is 29. Clara is 57. Anna returns younger than she was when Clara's children were born. She is effectively a generation removed from her twin sister. And if we push to the extremes of what might be physically achievable, 99.9% of light speed, where the Lorentz factor reaches 22.366, Anna experiences 1.4 years. 16 months. Barely more than 1 year of subjective time for a journey that spans 3 decades of Earth time. Anna returns essentially unchanged from when she left, still 26 years old, while Clara is 57. They are no longer sisters. They are barely recognizable to each other. Clara could be Anna's mother. She is old enough to be Anna's mother. This is the tragedy made explicit. The numbers are not hypothetical. They follow directly from experimentally verified physics. If we build spacecraft capable of reaching these velocities, and the laws of physics do not forbid it, only engineering challenges stand in the way, these time dilations will occur. They are not subject to debate or interpretation. They are as certain as gravity, as unavoidable as entropy. The emotional weight of this scenario is difficult to fully grasp. Imagine being Anna. You volunteer for a mission that will, you are told, age you by 20 years. A significant sacrifice, but tolerable. You are young. You will still have decades of life remaining when you return. But you are also told that everyone you know will age by 50 years. Your parents, already elderly, will almost certainly die while you are gone. Your siblings will become old. Your friends will have lived entire lives, marriages, children, careers, all the texture and detail of a human existence, while you were absent. You will return to find that time has not stopped. It has raced ahead, leaving you stranded in your own past, a relic, an anachronism. And imagine being Clara. You watch your sister leave, knowing intellectually that she will age more slowly, but unable to truly internalize what that means. Years pass. You marry. You have children. Your parents grow frail, then die. You attend their funerals without your twin sister. Your children ask about their aunt, the one in the photographs, the one who went to the stars. You tell them she is coming back. She is still out there, still traveling, still young. They will meet her someday. And then Anna returns. She steps off the spacecraft, 45 years old while you are 75. She looks at you and barely recognizes you. You are old. You are a stranger wearing the face of her sister, distorted by decades of time. She has missed your entire adult life. She was not there when you needed her. She was not there for any of it. And it is not her fault. She did not choose this. Physics chose it. The universe imposed this separation, encoded it in the curvature of spacetime, enforced it with mathematical rigor. The twin paradox is a thought experiment in mourning. It is mourning for time lost, for shared experiences that will never occur, for relationships severed not by death or distance but by velocity. It is mourning for a future that could have been, a future where both sisters aged together, where they shared the journey of life at the same pace, where they could have been old women together, reminiscing about their youth. That future is gone, erased by the decision to travel at relativistic speeds. And nothing can bring it back. This is not science fiction. This is the universe we inhabit. And if we choose to explore it, if we choose to travel among the stars at speeds significant enough to make such journeys feasible within human lifetimes, we will pay this price. Over and over. Every departure will be a partial death. Every return will be a reunion with ghosts. The travelers will age slowly. Everyone else will age normally. And the gap will widen with every journey, until the travelers are no longer part of the society they left behind, no longer connected to any living person who remembers their departure. They will become time exiles. And the universe will not care. Doubt is healthy. Doubt is essential. When confronted with claims as strange as time dilation, when told that moving clocks run slow, that twins age at different rates, that time itself is malleable, the rational response is skepticism. Show me the evidence. Prove it. Don't ask me to believe based on mathematical elegance alone. Physics is an empirical science. The universe does not care about our equations unless those equations make testable predictions that can be confirmed or falsified through observation. Time dilation has been tested, relentlessly, with precision that borders on absurdity. And every test, without exception, confirms what Einstein predicted in 1905. The muons testament is perhaps the most elegant of these confirmations, a natural experiment provided by the cosmos itself, requiring no particle accelerators or atomic clocks, only careful observation of particles raining down from the sky. Muons are elementary particles, siblings to electrons but heavier, about 207 times the electron's mass. They are unstable, decaying into electrons and neutrinos with a half-life of 2.2 microseconds as measured in their rest frame. This means that if you create a muon and observe it at rest, half of a large sample will decay within 2.2 microseconds. Wait another 2.2 microseconds and half of the remainder decay. Wait another interval and half again. The decay is exponential, probabilistic, governed by quantum mechanics, but statistically predictable. Muons are created continuously in Earth's upper atmosphere when cosmic rays, high-energy protons from deep space, collide with atmospheric nuclei. These collisions occur at altitudes of 15 to 20 kilometers, in the thin air where the atmosphere transitions toward the vacuum of space. The muons produced in these collisions are born moving at relativistic speeds, typically around 99.8% of the speed of light, propelled by the enormous energies of the cosmic ray collisions. And they head downward, toward Earth's surface, traveling through the thickness of the atmosphere. Here is the problem. At 99.8% light speed, a muon covers approximately 300 meters per microsecond. In its half-life of 2.2 microseconds, it should travel about 660 meters before half the population decays. In 4.4 microseconds, 2 half-lives, it should travel 1,320 meters, with only 1/4 of the original muon surviving. In 10 microseconds, it should travel about 3,000 meters, with less than 3% surviving. But the muons are created at 15,000 to 20,000 meters altitude. Even traveling at near-light speed, they should decay long before reaching the ground. We should detect almost no muons at sea level. The atmosphere should act as a shield, allowing the muons to penetrate a few thousand meters before they decay into electrons and neutrinos, their brief existence ending in the upper atmosphere. But we detect muons at sea level. Constantly. In abundance. Muons shower down on every square meter of Earth's surface, penetrating through the atmosphere, reaching the ground, passing through buildings and into underground detectors. The flux is substantial, about 1 muon per square centimeter per minute at sea level. These particles should not be here. They should have decayed kilometers above our heads. Their presence is impossible according to non-relativistic physics. The resolution is time dilation. The muons are moving at 99.8% light speed. At this velocity, the Lorentz factor is approximately 15.8. Time aboard the muon, the proper time in the muon's rest frame, runs 15.8 times slower than time on Earth. From our perspective, the muon's half-life is not 2.2 microseconds but 2.2 times 15.8, which equals about 34.8 microseconds. At near-light speed, the muon can travel 34.8 microseconds times 300 meters per microsecond, which equals approximately 10,440 meters before half the population decays. This is enough. This allows the muons to reach sea level. Half will decay en route, but half will survive, and we detect them. From the muon's perspective, and yes, we can speak meaningfully about the muon's perspective even though muons are not conscious, the journey is different. The muon experiences only 2.2 microseconds of proper time. It does not age slowly. It ages normally in its own frame. But from the muon's perspective, the distance it must travel is length contracted. The 15,000 meter thickness of the atmosphere is contracted by the Lorentz factor to 15,000 divided by 15.8, which equals about 950 meters. The muon travels 950 meters in 2.2 microseconds in its frame, which it can easily accomplish at near-light speed and reaches the ground before decaying. Both perspectives are correct. From Earth's frame, the muon lives longer due to time dilation. From the muon's frame, the atmosphere is thinner due to length contraction. The invariant fact, the thing both frames agree on, is that muons reach the ground. The mechanism by which this happens depends on your reference frame, but the outcome is consistent. This is the power and elegance of relativity. Different observers describe the same events using different combinations of space and time, but they agree on the physical results. The muon flux was first measured carefully in the 1940s and has been confirmed countless times since. The agreement between prediction and observation is excellent. If time dilation did not occur, muon detection rates at sea level would be reduced by factors of hundreds or thousands. We would detect only the rare, improbably lucky muons that happen to survive many half-lives through statistical fluctuation. Instead, we detect muons in exactly the numbers predicted by time dilation. The muons themselves, in their brief microsecond lives, testify to the reality of relativistic effects. But the muon is not the only witness. Atomic clocks provide even more precise confirmation. In 1971, physicist Joseph Haefel and astronomer Richard Keating performed an experiment of beautiful simplicity. They took 4 cesium beam atomic clocks, among the most precise timekeeping devices available at the time, and flew them around the world on commercial airliners. 2 flights, one eastward, one westward. The clocks were then compared to reference clocks that remained on the ground at the United States Naval Observatory. The results were striking. The eastward traveling clocks, which moved faster relative to Earth's surface due to the planet's rotation, lost time compared to the ground clocks, 59 nanoseconds on average. The westward traveling clocks, which moved slower relative to the surface, the airplane's westward velocity partially cancelled Earth's eastward rotation, gain time 273 nanoseconds on average. These effects are tiny, billionths of a second, but they are measurable, and they match the predictions of special relativity, combined with general relativistic effects due to the altitude change, which also affects time. The Hayfel-Keating experiment was controversial initially. Atomic clocks in 1971 were less stable than modern versions, and the error bars were comparable to the measured effects. But subsequent experiments with better clocks, including modern GPS satellites, have confirmed the results beyond any reasonable doubt. GPS satellites orbit at about 20,000 kilometers altitude, moving at approximately 14,000 kilometers per hour. They experience both special relativistic time dilation, due to their velocity, and general relativistic time dilation, due to being in a weaker gravitational field than Earth's surface. The special relativistic effect causes the satellite clocks to lose about 7 microseconds per day. The general relativistic effect causes them to gain about 45 microseconds per day. The net effect is a gain of 38 microseconds per day. 38 microseconds per day does not sound like much, but GPS navigation relies on timing signals that travel at light speed. A timing error of 38 microseconds corresponds to a position error of 11 kilometers. If GPS satellites did not correct for relativistic effects, if engineers had ignored Einstein and simply synchronized the satellite clocks to ground clocks, the system would accumulate errors of 11 kilometers per day. Within a week, GPS navigation would be useless, off by dozens of kilometers, unable to provide accurate location data. Every smartphone, every navigation system, every aircraft using GPS would drift into error. But GPS works. It works because the satellite clocks are programmed to run slightly slower than ground clocks, pre-compensating for the relativistic effects they will experience in orbit. The engineers who designed GPS did not believe in relativity as a philosophical preference. They believed in it because the mathematics predicted specific, quantifiable errors, and those errors were confirmed in early satellite tests. Relativity is not an abstract theory. It is an engineering correction factor, implemented in firmware, running on every GPS satellite currently in orbit. Particle accelerators provide yet another confirmation. At facilities like CERN, physicists accelerate protons to 99.9999991% of the speed of light in the Large Hadron Collider. At this velocity, the Lorentz factor is about 7,461. The protons should experience time 7,461 times slower than stationary observers. And they do. Unstable particles created in collisions last 7,461 times longer, as measured by stationary clocks, than their rest frame half-lives predict. Particles that should decay in nanoseconds survive for microseconds, traveling meters instead of millimeters before decaying. The accelerator itself had to be designed with relativity in mind. The magnetic fields that steer the protons must account for their relativistic mass increase, or the protons would crash into the walls of the beam pipe. Every particle physics experiment confirms time dilation. Every GPS satellite confirms time dilation. Every cosmic ray muon confirms time dilation. The experimental evidence is overwhelming, redundant, impossible to dismiss. Time dilation is not a hypothesis. It is an observed phenomenon, measured to high precision, confirmed across multiple independent experimental methods, woven into technologies that billions of people use daily. The muon's testament is this: I should not be here. I should have decayed kilometers above your head. But I reached the ground because time itself bent around my velocity, stretched my brief life long enough to complete the journey. I am proof, written in particle tracks and scintillation flashes, that time is not absolute. I am evidence, raining down from the sky every second of every day, that Einstein was right. And if time dilation is real for muons, if it is real for atomic clocks on airplanes, if it is real for GPS satellites orbiting Earth, then it is real for spacecraft traveling at relativistic speeds. It is real for astronauts who venture into the cosmos. It is real for the twin sisters, for the traveler and the homebody, for everyone who moves fast and everyone who stays still. The universe does not make exceptions. The laws are universal, and the price is always paid. Let us climb the ladder. Let us begin with speeds we understand, speeds that feel human, and ascend step by step into the relativistic regime where intuition fails and mathematics becomes the only guide. Each rung represents a velocity, a fraction of light speed, and with each rung the consequences grow more severe, the time dilation more pronounced, the separation between traveler and homebody more catastrophic. Rung 1, 1% of light speed, 3,000 kilometers per second. This is still unimaginably fast by human standards. The Apollo spacecraft that carried humans to the moon reached about 11 kilometers per second at maximum velocity. 3,000 kilometers per second is 273 times faster. This is the velocity of nothing humans have ever built, nothing we have even seriously proposed building with current technology. And yet, relativistically speaking, this is barely moving. The Lorentz factor at 1% light speed is 1.00005. Time dilation is essentially negligible. For every 100,000 seconds that pass on Earth, the traveler experiences 99,995 seconds. The difference is 5 seconds per 100,000, or 0.005%. For a 10-year journey, the traveler would age about 16 hours less than someone on Earth. Noticeable if you're comparing precise atomic clocks. Irrelevant if you're measuring human lifespans. At this velocity, you could reach Mars at its closest approach, about 55 million kilometers, in roughly 5 hours. You could reach Jupiter, 778 million kilometers at its closest, in about 3 days. You could reach Neptune, 4.3 billion kilometers, in less than 3 weeks. The solar system becomes accessible on human timescales. You could explore the outer planets and return within the same year. But the stars remain untouchable. The nearest star, Proxima Centauri, lies 40 trillion kilometers away. At 1% light speed, the journey takes 424 years. You would die of old age long before you reached even the nearest stellar neighbor. Rung 2, 10% of light speed, 30,000 kilometers per second. Now we enter the realm of serious proposals. Project Daedalus, a British interstellar society study from the 1970s, envisioned an unmanned spacecraft using nuclear pulse propulsion to reach 12% light speed. The Breakthrough Starshot initiative, funded by Russian billionaire Yuri Milner, proposes using ground-based lasers to accelerate tiny spacecraft to 20% light speed. These are not fantasies. These are engineering studies, backed by physics, limited only by technological and economic constraints. At 10% light speed, the Lorentz factor is 1.005. Time dilation is now 0.5%. For a 10-year journey, the traveler ages about 18 days less than someone on Earth. Still small, but no longer negligible. If you departed at age 25 and traveled for 40 years, you would return at age 65 while Earth aged 65.7 years. Everyone you know would be slightly older than you expected. Friends in their mid-60s would be approaching 70. The difference is noticeable, unsettling, but not devastating. At this velocity, Proxima Centauri is 42.4 years away. A human lifetime, barely. A crew departing in their 20s would arrive in their 60s, too old to establish a colony, too worn to explore. But unmanned probes could make the journey. Data could be transmitted back to Earth, arriving 4.24 years after the probe's arrival. Humanity could receive images of an exoplanet, confirming or denying the presence of life, within half a century of launch. The stars become imaginable, if not yet practical. Rung 3, 50% of light speed, 150,000 kilometers per second. This is where relativity begins to bite. The Lorentz factor is 1.155. Time dilation is 15.5%. For every 10 years that pass on Earth, the traveler experiences 8.66 years. The gap is now substantial. A 40-year Earth time journey means the traveler ages only 34.6 years. A 25-year-old departing astronaut returns at age 59.6 while Earth has aged 40 years, reaching 65. Parents who were elderly at departure are long dead. Siblings are senior citizens. The astronaut has lost years, Measurable years, irreplaceable years. At half-light speed, Proxima Centauri is 8.48 years away in Earth's frame. The traveler experiences 7.35 years. A round trip, 14.7 years for the traveler, 17 years for Earth. Doable within a human career. An astronaut could volunteer, train, travel, and return before retirement age. But the social cost is severe. A spouse who waits will be 2 years older. Children will be 2 years further into their lives. Friendships will strain under the weight of asynchronous aging. The astronaut will return to find the world subtly but irrevocably changed. Rung 4, 90% of light speed, 270,000 kilometers per second. We are now deep in the relativistic realm. The Lorentz factor is 2.294. Time passes at 43.6% the rate for travelers compared to those at rest. For every 10 years on Earth, the traveler experiences 4.36 years. The divergence is no longer subtle. It is brutal, undeniable, impossible to ignore. A journey to a star 50 light-years distant takes 55.56 years in Earth's frame, accounting for acceleration and deceleration. The traveler experiences 24.2 years. A 25-year-old astronaut departs and returns at age 49.2. Earth has aged 55.56 years. The astronaut is middle-aged. Everyone they knew is elderly or dead. Their parents are certainly dead. Their siblings are in their 70s or 80s. Their children, if they had any before departing, are now older than the astronaut. The astronaut has become their own grandchild's contemporary. The family tree has inverted. At this velocity, the galaxy begins to open. Stars within 100 light-years, thousands of stellar systems, become reachable within a human lifetime of travel time. But the cost is exile. The astronaut becomes a time refugee, cut off from their origin era, adrift in a future they did not live through. Every journey is a one-way trip in a temporal sense. You can return to Earth, but you cannot return to your time. The Earth you left is gone, replaced by a world that has aged decades while you aged years. Rung 5, 99% of light speed, 297,000 kilometers per second. The Lorentz factor is 7.089. Time runs at 14.1% the normal rate for the traveler. 10 years on Earth equals 1.41 years aboard the spacecraft. The ratio is now staggering. A journey to a star 500 light-years distant, deep into the galaxy, well beyond the local neighborhood, takes 505 years in Earth's frame. The traveler experiences 71.2 years. A 25-year-old departs and arrives at the destination at age 96.2, ancient, at the edge of death, but they arrive. Meanwhile, Earth has moved through 505 years of history. Nations have risen and fallen. Languages have evolved. Technology has advanced beyond recognition. If the astronaut turns around and comes back immediately, another 505 years pass on Earth. A round trip, 142.4 years for the traveler, 1,010 years for Earth. A millennium. No one the traveler knew is alive. No one from their century is alive. The species itself may have evolved, split into subspecies, or transcended biology entirely. The traveler returns to a world that is alien, incomprehensible, a future so removed from their origin that they might as well have traveled to another planet. And yet, subjectively, they aged only 142 years. Long, yes, but within the range of theoretical human longevity with advanced medicine. They are not old. The world is old. The traveler is a living fossil, a representative of an extinct era, preserved by velocity. Rung 6, 99.9% of light speed. The Lorentz factor is 22.366. Time for the traveler is 4.47% of Earth time. 1 year aboard the spacecraft equals 22.366 years on Earth. A 10-year subjective journey corresponds to 224 years of Earth time. The astronaut ages 1 decade. Civilization ages 2 centuries. At this velocity, the galaxy is yours. The Milky Way is 100,000 light-years across. Traveling at 99.9% light speed, you could cross the entire galaxy in about 4,472 years of subjective time. Impossible for a single human lifetime, but perhaps tolerable for a generation ship where children are born, grow, and die during the journey. Except that Earth, by the time you arrive, has aged 100,000 years. Modern humans, Homo sapiens, are only 300,000 years old. 100,000 years is 1/3 of our species' entire existence. You would return to find humanity unrecognizable, if humanity still exists at all. Rung 7, 99.99% of light speed. The Lorentz factor is 70.712. Time is 1.41% of normal. 1 year equals 70.712 Earth years. A subjective 10-year journey equals 707 Earth years. You age a decade. Civilization ages nearly a millennium. You could reach the Andromeda Galaxy, 2.5 million light-years distant, in 35,356 years of subjective time. Still too long for a human lifetime, but within the range of a well-designed generation ship. And when you arrive, Earth will have aged 2.5 million years. This is longer than our species has existed. Our ancestors 2.5 million years ago were Australopithecus, barely bipedal, more ape than human. You would return to find a world where humanity, if it survives, is as different from your era as we are from those ancient primates. Rung 8, 99.999999% of light speed, 8 nines. The Lorentz factor is 2,236. Time is 0.045% of normal. 1 year of travel equals 2,236 Earth years. A 10-year subjective journey equals 22,360 Earth years, longer than recorded human history. At this velocity, the observable universe opens. You could travel billions of light-years within a subjective human lifetime. You could visit distant galaxies, watch the cosmic web of structure unfold, see the universe as it exists far from our local region of spacetime. But you would never return. By the time you turned around, Earth would be millions or billions of years older. The Sun would be expanding into a red giant, incinerating the inner planets. Life on Earth, if it still exists, would have fled to the outer solar system or beyond. The planet itself might be gone, swallowed by the dying star, leaving only a faint memory of where humanity was born. This is the ladder. This is the progression from the merely fast to the relativistically extreme. Each rung increases the time dilation, increases the separation between traveler and homebody, increases the price paid in years lost, in connections severed, in the irrevocable alienation from the origin era. And notice, we have not violated any laws of physics. We have not exceeded light speed. We have not invoked wormholes or warp drives or exotic matter. We have simply climbed the velocity ladder that Einstein's equations provide, moving closer and closer to light speed, paying a steeper and steeper toll in time. The ladder has no top rung. You can always add another 9 to the velocity, 99.9999999% light speed, 99.9999999%, approaching light speed asymptotically but never reaching it. And with each additional 9, the Lorentz factor multiplies, the time dilation intensifies, the traveler's subjective time compresses while Earth's time expands. There is no limit to how much time you can skip. You could, in principle, travel for 1 subjective year and return to find the universe approaching heat death, the last stars flickering out, the cosmos cold and dark and empty. But you cannot travel backward. You cannot undo the journey. You cannot reclaim the lost time. The ladder only goes up, only carries you further into the future, never back to the past. And once you climb it, once you step onto that first rung and accelerate away from Earth, you commit yourself to the journey. You become a time traveler, willing or not. And the universe, indifferent and mathematical, extracts its price. The ladder exists. The mathematics are clear. Time dilation is real, verified, inescapable. But there is another wall, another barrier, another prison that confines us. We cannot reach these velocities. We cannot climb the ladder. The run's are there, tantalizingly visible in the equations, but we lack the strength to pull ourselves up. This is the propulsion apocalypse, the engineering nightmare that stands between our current capabilities and the relativistic velocities needed to make time dilation relevant. Let us begin with the tyranny of the rocket equation. The rocket equation, formulated by Konstantin Tsiolkovsky in 1897, is beautiful in its simplicity and devastating in its implications. It states that the change in velocity a rocket can achieve is equal to the exhaust velocity of its propellant multiplied by the natural logarithm of the initial mass divided by the final mass. In symbols, V equals V_E times ln, m_initial, m_final. This seems innocuous until you examine what it actually means. The exhaust velocity, how fast the propellant exits the rocket, is determined by the energy released per unit mass of fuel. Chemical rockets, burning hydrogen and oxygen, achieve exhaust velocities around 4.5 kilometers per second. This is excellent for reaching orbit, adequate for traveling within the solar system, and utterly inadequate for relativistic speeds. To reach even 1% of light speed, 3,000 kilometers per second, using chemical propulsion, the mass ratio would need to be astronomical. Let us calculate. We need V of 3,000 kilometers per second. The exhaust velocity is 4.5 kilometers per second. The mass ratio is therefore E caret 3004.5, which equals E caret 666.7, which is approximately 10 to the power of 289. This means your rocket would need to be 10 to the power of 289 times more massive at launch than at arrival. For every kilogram of payload, you would need 10 to the power of 289 kilograms of fuel. To put this in perspective, the observable universe contains approximately 10 to the power of 53 kilograms of matter. You would need 10 to the power of 236 observable universes worth of chemical fuel to accelerate 1 kilogram to 1% light speed using chemical rockets. This is not an engineering challenge. This is a mathematical impossibility. Chemical propulsion cannot take us to the stars. It cannot even get us close. Nuclear propulsion improves the situation marginally. Fission rockets, which use nuclear reactors to heat propellant, can achieve exhaust velocities around 8 to 10 kilometers per second. Better, but still catastrophically insufficient. To reach 1% light speed, the mass ratio is E caret 3009, which equals E caret 333.3, which is approximately 10 to the power of 144. Still impossible. Still requires more matter than exists in trillions of galaxies. Fusion propulsion, the holy grail of rocket designers, could theoretically achieve exhaust velocities around 3 to 5% of light speed, or 9,000 to 15,000 kilometers per second, by directing the energy from fusion reactions into thrust. This is a game changer. At 10,000 kilometers per second exhaust velocity, reaching 10% light speed requires a mass ratio of E caret 30,000,10,000 equals E cubed, almost equal to 20. For every kilogram of payload, you need 20 kilograms of fuel. Challenging but achievable. A 1,000-ton spacecraft would require 20,000 tons of fusion fuel. Large, expensive, difficult, but within the realm of possibility for a sufficiently motivated civilization. But fusion propulsion remains theoretical. We have not yet achieved controlled fusion that produces net energy gain, much less weaponized it into a rocket engine. The engineering challenges are immense, confining plasma at millions of degrees, maintaining the reaction long enough to extract useful thrust, protecting the spacecraft from neutron radiation, preventing the engine from melting or vaporizing under the extreme conditions. Decades of research have brought us closer, but functional fusion rockets remain firmly in the future, perhaps decades away, perhaps longer. And even fusion propulsion fails at truly relativistic speeds. To reach 50% light speed using a fusion rocket with 10,000 kilometers per second exhaust velocity, the mass ratio is E caret 150,000,10,000 equals E to the power of 15, almost equal to 3.3 million. For a 1-ton payload, you need 3.3 million tons of fusion fuel. The spacecraft becomes a flying fuel tank, the payload a tiny speck buried deep within megatons of hydrogen. And to reach 90% light speed, the mass ratio is e to the power of 45, almost equal to 3.4 times 10 to the power of 19. Impossible again. The tyranny of the rocket equation reasserts itself. So engineers have proposed alternatives. Schemes that circumvent the rocket equation by not carrying all the fuel, by scavenging it from space, by pushing from behind rather than exhausting it from the rear. The Bussard ramjet, conceived by physicist Robert Bussard in 1960, is an elegant solution on paper. The spacecraft deploys a vast magnetic scoop, hundreds or thousands of kilometers wide, that collects hydrogen atoms from the interstellar medium as it flies. The hydrogen is funneled into a fusion reactor at the rear of the ship, where it is fused and expelled as thrust. The spacecraft becomes a cosmic vacuum cleaner, breathing the thin interstellar wind, using that wind as both fuel and reaction mass. The mass ratio problem disappears because you're not carrying fuel, you're collecting it en route. The problem is that interstellar space is nearly empty. The average density of hydrogen in the interstellar medium is about 1 atom per cubic centimeter. To collect meaningful amounts, your magnetic scoop must be enormous, perhaps 10,000 kilometers in diameter, sweeping through trillions of cubic kilometers of space per second. The magnetic field strength required is immense, the power consumption staggering. And even if you solve these problems, there's a deeper issue, the drag. As you scoop up hydrogen, you're colliding with it, transferring momentum to it, slowing yourself down. At low speeds, the fusion energy exceeds the drag and you accelerate. But calculations suggest that above a certain velocity, possibly around 10 to 20% light speed, the drag exceeds the thrust. The ramjet becomes a brake, slowing you down rather than speeding you up. The very mechanism that makes interstellar travel possible becomes the mechanism that prevents it. No Bussard ramjet has ever been built. The engineering challenges, creating and maintaining magnetic fields of that scale, achieving fusion ignition with the dilute, contaminated interstellar hydrogen, managing the radiation from the fusion reactions, are beyond current technology by orders of magnitude. It remains a beautiful idea, a theoretical possibility, but not a practical solution. Solar sails and laser sails offer another approach: don't carry fuel at all. Instead, use photon pressure, the momentum carried by light itself, to accelerate. A solar sail near Earth receives about 9 newtons of force per square kilometer of sail area from sunlight. This is tiny, but it's free, and it doesn't diminish with distance as long as you have a light source. For interstellar travel, you replace the sun with a powerful laser array stationed in the inner solar system, beaming gigawatts or terawatts of laser light at the departing spacecraft's sail. Breakthrough Starshot, the most serious proposal in this category, envisions a 1-gram spacecraft, essentially a computer chip with a camera attached to a 4-meter sail. A ground-based laser array producing 100 gigawatts of power beams light at the sail for several minutes, accelerating the tiny spacecraft to 20% light speed. At that velocity, it would reach Proxima Centauri in about 20 years, transmit images back to Earth, and complete humanity's first interstellar mission. The challenges are formidable. The laser array must be extraordinarily powerful. 100 gigawatts is roughly the electrical output of 100 nuclear power plants. The beam must remain focused over millions of kilometers, requiring adaptive optics that can compensate for atmospheric distortion in real time. The sail must be reflective, lightweight, and able to withstand the intense laser heating without vaporizing. The spacecraft must be miniaturized to 1 gram while still containing a camera, transmitter, power source, and navigation system. And there is no way to slow down. The spacecraft will scream past Proxima at 20% light speed, taking measurements during a brief flyby lasting hours, then continuing into interstellar space forever. But unlike fusion rockets and Bussard ramjets, laser sails are not purely theoretical. The physics is sound. The technology, while challenging, does not require new physics, only engineering advances in lasers, materials, and miniaturization. Breakthrough Starshot has funding, has scientists, has a roadmap. It might actually happen within the next few decades. We might actually launch our first interstellar probe. And yet, laser sails cannot carry humans. 1 gram is enough for a chip. It is not enough for a person, for life support, for radiation shielding, for food and water, and all the infrastructure required to keep a human alive for years or decades. To accelerate a crewed spacecraft using laser propulsion, you would need sails hundreds of kilometers across and laser arrays producing petawatts of power, 1,000,000 gigawatts, 1,000 times the total electrical output of human civilization. The scaling is brutal, perhaps insurmountable. Antimatter propulsion is the theoretically ideal solution. When matter and antimatter collide, they annihilate, converting 100% of their mass into energy according to Einstein's E equals mc squared. This is the highest possible energy density. No other reaction can extract more energy per unit mass. A kilogram of antimatter annihilating with a kilogram of matter releases 1.8 times 10 to the power of 17 joules, equivalent to 43 megatons of TNT, roughly the yield of the largest nuclear weapon ever detonated. With antimatter, you can achieve exhaust velocities approaching light speed itself. The photons and particles released in matter-antimatter annihilation travel at or near light speed. This makes the rocket equation favorable again. To reach 50% light speed with an effective exhaust velocity of 90% light speed, the mass ratio is E caret, 0.5 degrees Celsius 0.9 degrees Celsius, almost equal to E caret 0.56, almost equal to 1.75. For a 1-ton payload, you need 1.75 tons at launch, 750 kilograms of fuel, split equally between matter and antimatter. Doable. Practical. Within the range of engineering possibility. Except for one small problem, we cannot produce antimatter in meaningful quantities. Current production rates at CERN, the world's leading particle physics laboratory, are about 10 nanograms per year. At this rate, producing 1 gram of antimatter would take 100 million years. And even if we could produce it faster, storing it is nearly impossible. Antimatter annihilates on contact with matter, so it must be confined in electromagnetic traps, suspended in vacuum, never touching the walls of its container. The longest we have successfully stored antimatter is about 16 minutes for a handful of antihydrogen atoms. Storing kilograms for years-long space missions is science fiction, not science fact. And even if we solved production and storage, the cost would be astronomical. Current estimates suggest antimatter, if produced industrially, might cost $25 billion per gram. The 375 kilograms of antimatter needed for our 50% light speed journey would cost about $10 quadrillion, $10,000 trillion, roughly 100 times the global GDP. This is not a budget item. This is a civilization-scale resource allocation that would require the combined economic output of humanity for a century. So we are trapped. Chemical rockets, insufficient. Nuclear rockets, insufficient. Fusion rockets, theoretical and insufficient at high speeds. Bussard ramjets, theoretical and possibly self-defeating. Laser sails, possible for tiny probes, impractical for crewed missions. Antimatter, perfect in theory, impossible in practice. The propulsion apocalypse is not one barrier but many, layered defenses that the universe has erected against our ambitions. Each incremental improvement in propulsion technology pushes us a little further up the velocity ladder, but the exponential growth of the Lorentz factor means that each additional percentage point of light speed requires exponentially more energy, exponentially more fuel, exponentially more engineering sophistication. We are like climbers attempting to scale a cliff where each handhold is twice as difficult as the last, where the summit recedes faster than we can climb, where exhaustion and limitation and the fundamental constraints of physics conspire to keep us forever near the bottom. This is why, despite a century of spaceflight, despite landing on the moon and sending probes to the edge of the solar system, we have not built a starship. This is why the stars remain out of reach. Not because we lack ambition or courage or vision, but because the universe itself resists. The energy requirements are too high. The engineering challenges are too severe. The economic costs are too staggering. And so we remain here, on this pale blue, looking up at the night sky, knowing that time dilation could let us reach those stars within our lifetimes, but unable to build the engines that would carry us there. The ladder exists. We simply cannot climb it. And this, more than any other single factor, is why the tragedy of time dilation remains theoretical rather than practical. We have not yet faced the choice between staying home and losing decades to relativistic travel, because we cannot yet travel relativistically. The propulsion apocalypse protects us from the temporal consequences of our ambitions. For now, let us make it concrete. Let us design a mission, not a fantasy, but a realistic engineering study using technologies that are at least theoretically achievable. Let us send humans to Proxima Centauri b, the nearest confirmed exoplanet, orbiting the nearest star beyond our Sun. Let us calculate what it would cost, how long it would take, and what price the crew would pay in time. Proxima Centauri lies 4.24 light-years from Earth, approximately 40 trillion kilometers. Proxima Centauri b, discovered in 2016, orbits within the star's habitable zone, the region where liquid water could exist on the surface. It is 1.17 times Earth's mass, rocky, possibly with an atmosphere, possibly with oceans. It is the closest world beyond our solar system where life might exist, where human colonization might be possible. If we are ever to reach another star, Proxima is the obvious first target. Our spacecraft will use a fusion drive, the most optimistic propulsion technology that doesn't require antimatter or magical new physics. Let us assume we have solved the engineering challenges, that we have a working fusion reactor that can achieve 5% of light speed exhaust velocity, 15,000 kilometers per second, and that we can sustain this thrust for years. Let us assume a spacecraft mass of 10,000 tons at launch, including fuel, habitat, life support, radiation shielding, and a crew of 100 people. The mission profile is straightforward. Accelerate at a constant 0.3 g, approximately 3 meters per square second, for the first half of the journey, providing artificial gravity for the crew and steadily increasing velocity. At the midpoint, flip the spacecraft and decelerate at 0.3 g for the second half, arriving at Proxima with zero relative velocity. This constant acceleration profile is comfortable for humans. 0.3 g is sufficient to prevent muscle and bone loss while being mild enough that even elderly or infirm crew members can tolerate it for years. Let us calculate the travel time. Under constant acceleration, the relativistic equations give us the proper time experienced by the crew, tau, and the time elapsed on Earth, t. For a one-way journey of 4.24 light-years under constant 0.3 g acceleration and deceleration. Earth time, approximately 6.5 years. Proper time, crew approximately 5.8 years. The difference is relatively small, about 8 months, because we never reach extremely high velocities. The peak velocity at the midpoint is about 30% of light speed, where the Lorentz factor is only 1.05. Time dilation is present but modest. The crew ages 5.8 years while Earth ages 6.5 years. The social cost is tolerable. Family members age 8 additional months. Children grow 8 months older than expected. Parents decline 8 months further. This is noticeable, emotionally difficult, but not devastating. But the mission does not end at arrival. After exploring the Proxima system, let us allocate 2 years for orbital surveys, landing missions, sample collection, and scientific research. The crew must return. The return journey is identical to the outbound, 5.8 years crew time, 6.5 years Earth time. Total mission duration. Crew ages, 5.8 plus 2 plus 5.8 is equal to 13.6 years. Earth ages, 6.5 plus 2 plus 6.5 is equal to 15 years. The crew departs at age 35, on average, and returns at age 48.6. Earth has aged 15 years. They are now 50 years old. The difference is 1.4 years. Their children, who were 10 at departure, are now 25. The crew missed their children's teenage years, their high school graduations, possibly their college years and early careers. They missed weddings, funerals, the births of grandchildren. They missed 15 years of life on Earth, compressed into 13.6 years of their own experience. The temporal wound is real but survivable. Relationships can be maintained across a 1.4-year time gap. The crew can reintegrate into society. They are not aliens. They are not exiles. They are simply astronauts who were away for a very long mission. But now let us examine the cost. How much fuel does this require? The rocket equation, even with fusion propulsion, is unforgiving. To accelerate a 10,000-ton spacecraft to 30% light speed, then decelerate, then accelerate back, then decelerate again, requires a staggering amount of energy. Detailed calculations using relativistic rocket equations suggest a fuel mass of approximately 100,000 tons of fusion fuel, deuterium and helium-3, for the entire mission. The spacecraft at launch would be 110,000 tons, a flying fuel tank with a small habitat module attached. Where do we obtain 100,000 tons of helium-3? Earth has almost none, a few hundred kilograms at most, painfully extracted from natural gas deposits. The Moon has more, embedded in the regolith from billions of years of solar wind bombardment. Mining and refining 100,000 tons of helium-3 from lunar soil would require a massive industrial infrastructure on the Moon: strip mines, refineries, transport systems, representing an investment of trillions of dollars and decades of development. The economic cost of the mission would be comparable to the Apollo program, but sustained for 30 to 40 years instead of a decade. Call it $1 to $2 trillion in current dollars. Not impossible, but requiring a level of societal commitment we have not seen since the Cold War space race. And this is for a single mission, a single spacecraft, a single crew of 100 people sent to a single star. To establish a meaningful presence beyond the solar system, to send dozens or hundreds of missions, to create a true interstellar civilization, we would need to scale this effort by orders of magnitude. The resources required, the energy, the materials, the industrial capacity, would dominate human civilization for centuries. We would become a species whose primary purpose is building starships, whose economy revolves around the mining of helium-3 and the construction of fusion drives. And all of this, the trillion-dollar budgets, the decades of development, the strip mining of the Moon, to achieve a 1.4-year time dilation over a 15-year mission. The temporal benefit is minimal. Time dilation is barely relevant at these velocities. To make time dilation significant, to achieve the dramatic effects we discussed earlier, traveling for years while Earth ages for centuries, we must go faster. Much faster. Let us recalculate the mission at 80% light speed, where time dilation becomes substantial. Same mission profile: accelerate, coast, decelerate. But now we maintain 1g acceleration for the entire journey, providing Earth normal gravity and reaching far higher velocities. At 80% light speed. Earth time, approximately 5.5 years. Proper time, crew approximately 3.5 years. Now the difference is significant, 2 years. But the fuel requirements become absurd. To reach 80% light speed, even with fusion propulsion, the mass ratio climbs to e to the power of 8, almost equal to 3,000. A 10,000-ton spacecraft requires 30 million tons of fuel. This is not a spacecraft. This is a small asteroid, hollowed out, filled with fusion fuel, with a tiny crew module buried somewhere inside. The engineering challenges, storing, managing, and burning 30 million tons of deuterium and helium-3 over several years, are beyond anything humanity has attempted. And at 90% light speed, where Earth ages 5.5 years while the crew ages 2.5 years, the mass ratio is e to the power of 15, almost equal to 3.3 million. The spacecraft requires 33 billion tons of fuel. This is a moon. A small moon, hollowed and repurposed, accelerated to relativistic speeds, carrying a crew of 100 people in a module the size of a house buried deep in the Moon's interior. We cannot do this. The scaling defeats us. Every incremental increase in velocity, every additional percentage point toward light speed, multiplies the fuel requirements exponentially. And the universe offers no loopholes, no shortcuts, no way to circumvent the rocket equation's tyranny. So the mission to Proxima, if it ever happens, will likely proceed at modest velocities, 10% to 30% of light speed, where fuel requirements are challenging but achievable, where time dilation is present but modest, where the crew can realistically hope to return to a society they still recognize. The journey will take years, possibly decades. The crew will age nearly as much as Earth does. And the tragedy of time dilation will remain theoretical, a mathematical curiosity, a phenomenon we can calculate but never fully experience. Unless we find another way. Unless we abandon the rocket equation entirely. Unless we discover or invent propulsion technologies that don't require carrying fuel, warp drives, wormholes, reactionless drives, physics we haven't yet imagined. These possibilities hover at the edge of theoretical respectability, neither proven nor disproven, tantalizing in their implications and frustrating in their elusiveness. But for now, with the physics we know and the engineering we can imagine, Proxima Centauri remains just barely out of reach. We can see it in our telescopes. We can detect its planet with our instruments. We can calculate what it would take to go there. And we can conclude, reluctantly, that we are not yet ready. The propulsion apocalypse holds us here, on this world, looking outward, waiting for the breakthrough that will let us finally climb the ladder and pay the price that velocity demands. The journey to Proxima is a case study in despair, not because it's impossible, but because it's almost possible. We can see the path. We can sketch the engineering. We can write the equations. But we cannot yet build the machines. And so we wait and dream and calculate, hoping that someday, perhaps in our lifetimes, perhaps in our children's, perhaps never, we will find the will and the means to attempt the journey. And when we do, when that first crew departs for Proxima, they will carry with them the knowledge that they are leaving everyone they love behind. Not in space, but in time. They will age more slowly. Everyone else will age normally. And when they return, if they return, they will find the world changed, aged, moved on without them. This is the price. This is the covenant. This is what it means to reach for the stars. Now let us abandon caution. Let us imagine that we have solved the propulsion problem, that fusion or antimatter or some as yet undiscovered energy source allows us to accelerate to extreme relativistic velocities, 99% of light speed or higher. Let us send a mission not to the nearest star but to the nearest galaxy. Let us send humans to Andromeda. The Andromeda galaxy lies 2.5 million light-years from Earth. It contains 1 trillion stars, twice as many as the Milky Way. It is the most distant object visible to the naked eye, a faint smudge of light in the autumn sky, the closest major galaxy to our own. In cosmic terms, Andromeda is our neighbor. In human terms, it is impossibly, incomprehensibly distant. At 99.9% of light speed, with a Lorentz factor of 22.366, a one-way journey to Andromeda takes. Earth time, 2.5 million years. Proper time, crew 111,800 years. More than 100,000 years of subjective time. No human lives that long. No spacecraft could function for that duration. The mission is impossible with a single crew, even accounting for relativistic time dilation. But suppose we build a generation ship, a vessel large enough to support a self-sustaining population of thousands, where generations are born, live, and die during the journey. The ship becomes a world unto itself, a traveling civilization, its inhabitants knowing only the interior of the vessel, the distant stars ahead and behind, the endless years of transit. And suppose we accelerate harder, reaching 99.99% of light speed, where the Lorentz factor is 70.712. No. Earth time, 2.5 million years. Proper time, crew 35,356 years. 35,000 years. This is the entire span of recorded human history from the cave paintings at Chauvet to the present day. It is still impossibly long for a single human life, but perhaps tolerable for a civilization. The ship becomes a nation, its population in the tens of thousands, its culture evolving independently from Earth, its government and laws and traditions adapting to the unique constraints of relativistic travel. Children born aboard the ship grow up knowing they will die aboard the ship, as will their children and grandchildren for 1,000 generations. The journey becomes existence itself. Andromeda is not a destination but an abstract promise, a theological concept, the heaven their descendants will reach after eons of travel. And what of Earth? While the crew ages 35,356 years, Earth ages 2.5 million years. This is not a separation measurable in generations. This is geological time. This is evolutionary time. Consider what Earth has experienced in the last 2.5 million years, the emergence of the genus Homo, the evolution from Australopithecus to Homo habilis to Homo erectus to Homo sapiens, the Ice Ages, the glacial cycles, the migration out of Africa, the development of language, tools, culture, civilization, the rise and fall of empires, the scientific revolution, the industrial revolution, the atomic age, the information age. All of this, all of human history and prehistory, compacted into the time that elapses on Earth while the Andromeda mission is in transit. Now extrapolate forward. What will Earth look like 2.5 million years in the future? We cannot know. We can barely imagine. Will Homo sapiens still exist? Will we have evolved into something else, post-human, transhuman, unrecognizable? Will we have spread across the galaxy, built a Dyson swarm around the Sun, transcended biology entirely and uploaded ourselves into computational substrates? Will we have destroyed ourselves in nuclear war or environmental collapse? Will Earth itself still be habitable, or will climate change or asteroid impacts or stellar evolution have rendered it uninhabitable? The crew departing for Andromeda cannot answer these questions. They know only that they are leaving Earth behind in a way that is fundamentally different from any journey humanity has undertaken before. Previous explorers, the Polynesians crossing the Pacific, the Europeans sailing to the Americas, left their homelands knowing they would never return, but they remained part of the same species, the same epoch, the same historical moment. The crew of the Andromeda mission leaves not just their homeland but their era. They sever all connection to the timeline they came from. By the time they arrive, assuming they arrive, Earth will have moved through deep time, through evolutionary time, through cosmological time. And if they turn around and come back, another 2.5 million years elapses on Earth. Another 35,356 years for the crew. Round trip, 70,712 years crew time, 5 million years Earth time. The Sun itself will have noticeably evolved. It brightens by approximately 10% every billion years as it ages, fusing hydrogen into helium, gradually increasing its luminosity. Over 5 million years, the increase is small, about 0.05%, but measurable. Earth will be slightly warmer. The climate will have shifted. The continents will have drifted, not much, perhaps 100 kilometers, but enough to alter coastlines and ocean currents. And humanity? If humanity survives at all, it will be unrecognizable. The crew will return to find their descendants, if descendants is even the right word after 5 million years of evolution, changed beyond comprehension. New species may have emerged from the Homo sapiens lineage. Or perhaps intelligence has transcended biology entirely, existing as patterns of information in vast computational networks, no longer bound to flesh, no longer mortal in any meaningful sense. The crew, aging normally in their reference frame, will emerge from their ship having lived full lives, born, grown, loved, aged, died, been replaced by children and grandchildren for 1,000 generations. They will have their own history, their own culture, their own identity separate from Earth. They will be aliens returning to humanity, bearing news of Andromeda, carrying stories of what they found, of the stars they saw, of the worlds they passed. But the humanity they left behind is gone. The Earth they knew is gone. They are strangers in a strange land, returnees from a journey so long that the very definition of home has become meaningless. This is the Andromeda Covenant. You may attempt the journey, but you must understand that you are not traveling to another galaxy. You are traveling to another epoch. You are leaving your species behind, not in space, but in time. You will never rejoin the timeline you departed from. You will arrive in a future so distant that nothing you knew will remain. No buildings, no nations, no languages, possibly no recognizable biology. You will be time travelers, flung forward by the mechanism of velocity, unable to return not because the journey is impossible but because the destination, the temporal destination, no longer exists. Why would anyone accept such a covenant? Why would a crew volunteer for a mission that guarantees their exile not just from their planet but from their entire era? Perhaps for the same reasons explorers have always accepted exile: curiosity, ambition, the desire to see what lies beyond the horizon. Perhaps because the Andromeda mission, despite its incomprehensible duration and its severing of all temporal ties, offers something that staying on Earth cannot: true exploration, the genuine unknown, the chance to see another galaxy not through telescopes but with human eyes. Or perhaps because, by the time we are capable of mounting such a mission, staying on Earth will no longer be viable. Perhaps environmental collapse or resource depletion or existential threats will make emigration necessary. Perhaps the Andromeda mission will be an arc, a desperate attempt to preserve some fragment of humanity by sending it into the void, accepting the temporal cost because the alternative is extinction. But let us not romanticize this. The Andromeda Covenant is not an adventure. It is a sentence. It is the acceptance of absolute exile, the willing embrace of temporal solitary confinement. The crew will know, as they depart, that everyone they have ever known will die. That Earth will age 2.5 million years. That they will never return to their time. And they will go anyway, because the alternative, staying behind, remaining anchored to their era, living and dying within a single century, is somehow less bearable than the prospect of eternal forward motion through time. This is what relativistic travel offers, not a shortcut to the stars, but a mechanism for abandoning your epoch. Not a bridge between worlds, but a chasm between eras. Not exploration, but exile. And the universe, indifferent as always, permits this. The equations allow it. The physics enables it. The only question is whether we will ever possess the technology and the will to pay the price. The Andromeda Covenant awaits. It has always awaited. It will always await. And if we sign it, if we build the ships and recruit the crews and launch them into the void, we will be sending not explorers but refugees, not into space but into time, not toward a destination but away from everything they have ever known. This is the price of reaching Andromeda. This is the cost of truly relativistic travel. This is what it means to move fast enough that time itself fractures and you fall through the cracks into a future that was never meant to be yours. There are losses we can measure. The death of a parent, we mark it with a date, a funeral, a gravestone. The end of a marriage, we document it with papers, divide assets, establish custody. The loss of a job, a home, a friendship, each has its rituals, its processes, its stages of grief that have been studied and catalogued by psychologists. We understand these losses. We have words for them. We have support systems designed to help people navigate them. But there is no word for the loss that occurs when you leave Earth at relativistic velocity. There is no ritual for mourning people who are still alive but aging faster than you, drifting away from you in time rather than space. There is no support group for astronauts who return to find their children older than they are, their parents long dead, their entire social world dissolved by decades of time that passed while they were gone. This is the relativity of loss. Not the physics. We have covered the physics exhaustively, but the human dimension, the psychological toll, the emotional cost that cannot be calculated in Lorentz factors and time dilation ratios but only in broken relationships, missed moments, accumulated absences that transform into a chasm of incomprehension. Imagine you are 25 years old. You have a 5-year-old daughter. She is bright, curious, fascinated by the stars. When you tell her you are going on a long mission, years away, she doesn't fully understand. 5-year-olds live in the eternal present. Years is an abstract concept. She knows only that mommy or daddy is leaving, and it makes her sad, but she accepts it the way children accept things they cannot change. You depart. The mission is 10 years subjective time, traveling to a star system 50 light-years distant at 90% light speed. You know the numbers. You have done the math. 10 years for you. 55 years for Earth. You will age 10 years. Your daughter will age 55 years. When you return, you will be 35. She will be 60. Your daughter will be elderly. She will be old enough to be your mother. But knowing this intellectually is different from experiencing it emotionally. During the journey, you live normally. Days pass at their normal rate. You eat, sleep, work, exercise, maintain the ship systems. You think about your daughter often. You imagine what she is doing. Is she in school? Has she made friends? Does she still remember you? You record messages, video logs, letters, thoughts you want to share when you return. You tell her about the stars you are passing, the phenomena you observe, the beauty and terror of the relativistic void. You tell her you love her, that you miss her, that you are counting the days until you can hold her again. 10 years pass. Subjectively, this is a significant chunk of your life, nearly half of your adult existence up to the point of departure. You have changed. You have aged. The isolation and stress of the mission have left marks on your psyche. You have nightmares about equipment failures, about running out of supplies, about never reaching the destination. But you have also experienced wonder, the glory of approaching a new star system, the thrill of seeing worlds no human has ever observed, the profound satisfaction of pushing the boundary of human exploration further into the cosmos. And then you return. The journey home is another 10 years subjective, another 55 years Earth time. You emerge from the spacecraft 35 years old. You have been gone 20 years of your life. Earth has been gone 110 years. Your daughter is not there to greet you. She is not physically capable of traveling to the landing site. She is 115 years old, if she is still alive at all. Human lifespan, even with advanced medicine, rarely exceeds 120 years. You check the records. She died 3 years ago, Earth time. Peacefully, in her sleep, surrounded by her great-great-grandchildren. She had a good life, by all accounts. She married, had children, pursued a career, traveled the world, grew old with grace. She left behind letters for you, dozens of them, written over the course of her life, updated every few years, sealed and stored in a database with instructions to deliver them upon your return. You read the letters. The first few, written when she was young, are heartbreaking. She misses you. She doesn't understand why you had to go. She is angry, confused, sad. Her handwriting is childish, uneven, full of misspellings. Why did you leave? When are you coming back? I miss you, Mommy, Daddy. Please come home. Later letters, written in her 20s and 30s, are more resigned. She has accepted that you are gone, that you will not return until she is old. She has built a life without you. She married someone you never met. She had children you never held as infants. She sends you pictures, her wedding, her children, her grandchildren. She tells you about her career, her hobbies, the places she has traveled. She tells you that she understands, intellectually, why you went. She knows the mission was important. She knows you did not abandon her willingly. But she also tells you, honestly, that your absence shaped her life in ways she struggles to articulate. She felt abandoned, even though she knows you did not intend it. She felt orphaned, even though you were alive somewhere out there among the stars. The final letters, written in her 80s and 90s, are reflective, melancholic. She wonders if you will recognize her when you return. She wonders if you will be disappointed to find her so old, so different from the child you left behind. She wonders if the relationship can be salvaged, if you can bridge the gap of decades and generations, if you can find any common ground to stand on. She tells you she loves you, but the love is abstract now, a love for a memory, a love for the parent she knew as a child, not for the person you have become during your 10 years of travel. She is not sure she knows you anymore. She is not sure you know her. And then she dies. And you read her obituary. And you realize that you missed her entire life. You were not there when she learned to ride a bike, when she graduated high school, when she got her first job, when she fell in love, when she gave birth, when she held her grandchildren, when she buried her own parents, when she grew old and frail and contemplated her mortality. You were absent for all of it. Not because you were dead, not because you were indifferent, but because you were moving too fast, because time itself diverged, because the universe enforced a separation that no amount of love or intention could overcome. This is the relativity of loss. You have lost your daughter not to death. She lived a full life, but to time. She aged while you did not. She experienced 110 years of life while you experienced 20. And now she is gone, and you are 35, and the grief you feel is compounded by the knowledge that this was inevitable, calculable, predicted by equations you understood before you left. You did this. You chose this. You signed the covenant. But the equations cannot prepare you for the weight of it. The Lorentz factor is just a number. Time dilation is just a ratio. They cannot capture what it feels like to hold letters from your daughter spanning 80 years, to watch through photographs as she transforms from child to adult to elder, to see your own absence reflected in every milestone, every achievement, every moment you should have shared but didn't. And your daughter is not the only loss. Your parents are long dead. They died within 20 years of your departure, Earth time, passing away while you were still in transit to your destination. You were not there for their final years, their illnesses, their deaths. Your siblings are elderly or dead. Your friends are gone, scattered by time if not by death. The world you knew, the culture, the politics, the technology, has transformed. Languages have evolved. Cities have been rebuilt. Nations have risen and fallen. The music you loved is ancient history. The movies you watched are quaint artifacts. The idioms you spoke are archaic curiosities. You are a stranger in your own world, and the world is indifferent to your strangeness. It has moved on. It does not pause to accommodate you, to explain itself, to help you reintegrate. You are expected to adapt, to learn the new customs, to catch up on a century of history, to find your place in a society that has no place reserved for you. Some astronauts manage this. They are resilient, adaptable, psychologically robust. They mourn their losses, process their grief, and find new connections, new relationships, new purposes. They become historians, educators, translators between eras. They share their experiences with younger generations, offering perspective that no one else can provide. They find meaning in their dislocation, value in their unique position as bridges between past and present. But others do not manage. They sink into depression, isolation, despair. They cannot form new attachments because every new relationship is tainted by the knowledge that it will be temporary, that they could leave again on another mission and return to find everyone they care about aged or dead. They cannot find purpose because the world they are in is not the world they chose to live in. They chose their departure world, not this arrival world, and the difference is unbearable. Some turn to substance abuse. Some withdraw entirely, living as hermits, refusing to engage with a society that feels alien. Some, tragically, choose suicide, unable to bear the weight of their temporal exile. This is the human cost that the equations do not capture. The Lorentz factor tells you how much time will elapse. It does not tell you what that elapsed time will do to your relationships, your identity, your sense of self. It does not tell you what it feels like to become a ghost in your own life, present but disconnected, alive but not truly living, caught between an irretrievable past and an unwelcoming present. And here is the cruelest aspect. Time dilation is asymmetric. You experience it. Your loved ones do not. From their perspective, you left, time passed normally, and you returned. They aged. That is the extent of their experience. They cannot understand what it was like for you because they did not experience slower time. They aged normally, at the standard rate, and from their frame of reference, the journey was simply long. They do not grasp the phenomenological difference between aging 20 years because 20 years passed and aging 10 years while 110 years passed elsewhere. The subjective experience is alien to them. So you cannot explain it. You cannot make them understand. You can recite the physics, show them the equations, prove mathematically that you experienced less time than they did. But understanding the math is not the same as understanding the experience. And so you are alone in your grief, mourning losses that no one else can fully appreciate, carrying a burden that no one else can share. This is why some mission planners advocate for missions that do not return. Send the astronauts out, they argue, but do not bring them back. Let them establish colonies on distant worlds, building new civilizations disconnected from Earth, free from the temporal burden of return. The astronauts will still lose contact with everyone they knew. Radio signals will take years or decades to traverse the interstellar distances, but the loss will be mutual. Everyone will age together within their local community. There will be no asymmetry, no divergence, no relativity of loss. But this solution simply replaces one kind of loss with another. Instead of returning to find your daughter elderly, you leave knowing you will never see her again, that communication will be limited to time-delayed messages, that you are severing all ties permanently. It is not clear that this is better, only different. The loss is still profound. The grief is still real. Perhaps there is no good solution. Perhaps the relativity of loss is simply the price we must pay if we wish to travel among the stars at speeds significant enough to make the journey feasible within human lifetimes. Perhaps every interstellar mission will be a tragedy, a small death, a sacrifice of relationships and connections in service of exploration and discovery. Perhaps we will send our astronauts knowing we are sending them into exile, temporal refugees who will never truly come home, and we will honor their sacrifice the way we honor soldiers who die in war, not because we want them to suffer, but because we believe the mission justifies the cost. Or perhaps we will choose differently. Perhaps, when faced with the full emotional weight of relativistic travel, when forced to confront the human dimension of time dilation rather than the abstract mathematics, we will decide that the stars are not worth the price. That no scientific discovery, no new world, no expansion of human civilization justifies the destruction of families, the severing of bonds, the creation of temporal exiles who can never return to their era. This is the question we will face when, if, we develop the technology to travel at relativistic speeds. Not can we do it, but should we? Not what does it cost in fuel and energy, but what does it cost in human suffering? Not how fast can we go, but how much time are we willing to lose? The relativity of loss demands an answer. And the answer, whatever it is, will define what kind of species we become, one that reaches for the stars regardless of cost, or one that chooses connection over exploration, remaining anchored to our era even if it means remaining anchored to our planet. When people first learn about time dilation, a common response is to propose hibernation as a solution. What if we put the astronauts in cryogenic sleep, they ask. What if we slow their metabolism to nearly zero, freeze them, suspend them in a state between life and death? Then they wouldn't age during the journey. They could sleep for centuries and wake up unchanged, having aged only days or weeks despite the passage of decades or centuries outside. This proposal reveals a fundamental misunderstanding of what time dilation actually is and how it operates. And it is worth addressing this fallacy explicitly, because it highlights the difference between biological time and physical time, between aging and the passage of time itself. Hibernation, whether natural hibernation like bears in winter or speculative cryogenic suspension, is a process that slows biological functions. Metabolism drops. Heart rate decreases. Brain activity diminishes. Cellular processes that normally proceed at a certain rate proceed more slowly. An organism in hibernation ages more slowly in a biological sense because the biochemical reactions that constitute aging are rate-limited by temperature and metabolic activity. But hibernation does not affect the passage of time itself. A bear hibernating for 6 months experiences 6 months of physical time passing in the external universe. The Earth rotates 6 months' worth of days. The Sun moves 6 months along its path through the galaxy. Atomic clocks in the cave with the bear tick 6 months' worth of seconds. Time, as measured by any physical process not directly tied to the bear's metabolism, proceeds at its normal rate. Now consider time dilation. When you travel at relativistic speeds, you experience less proper time than stationary observers. This is not because your metabolism slows. This is not because your biological processes are suppressed. This is because time itself, physical time, measured by every possible clock, biological or otherwise, runs more slowly in your reference frame. An atomic clock traveling with you ticks fewer times. Radioactive atoms in your ship decay more slowly. Light waves oscillate through fewer cycles. Every physical process, without exception, proceeds at a reduced rate from the perspective of stationary observers. This is the crucial distinction. Hibernation affects biology. Time dilation affects physics. They are not equivalent. They are not even analogous. They operate on entirely different levels of reality. Suppose you put an astronaut in cryogenic suspension and send them to Proxima Centauri at 10% light speed. The journey takes 42.4 years in Earth's frame. The astronaut, frozen, does not biologically age. Their cells are suspended, their metabolism is zero, their body is preserved unchanged. But the spacecraft still experiences 42.4 years of proper time. Radiation still bombards the hull for 42.4 years. Components still degrade over 42.4 years. When the astronaut wakes at the destination, they are biologically young, but 42.4 years have passed in their reference frame. If they return immediately, another 42.4 years pass. Total, 84.8 years. If they had not hibernated, they would have aged 84.8 years during this time. Because they did hibernate, they aged 0 years biologically. But Earth still aged 84.8 years. Everyone they knew still aged 84.8 years. The temporal separation is the same. Now suppose instead you send the same astronaut to Proxima at 90% light speed without hibernation. The journey takes 6.5 years Earth time, 2.9 years proper time. The astronaut ages 2.9 years biologically because 2.9 years of physical time pass in their reference frame. Every clock on the ship, atomic, biological, quantum, registers 2.9 years. When they return, another 2.9 years pass. Total, 5.8 years proper time, 13 years Earth time. The astronaut has aged 5.8 years. Earth has aged 13 years. The temporal separation is 7.2 years. Compare these scenarios. Slow speed plus hibernation, 0 years biological aging, 84.8 years Earth time. Fast speed plus no hibernation, 5.8 years biological aging, 13 years Earth time. The fast speed with no hibernation results in less biological aging for the astronaut and less Earth time elapsed. Hibernation, in this comparison, accomplishes nothing useful. It preserves the astronaut's body but does not reduce the time elapsed on Earth. It does not solve the temporal separation problem. It does not prevent the loss of relationships, the aging of loved ones, the passage of decades or centuries that constitutes the true cost of interstellar travel. The only thing hibernation achieves is allowing the astronaut to survive longer journeys without aging biologically. If you are traveling at slow speeds, where time dilation is negligible, and the journey takes longer than a human lifespan, hibernation extends your effective lifespan to match the journey duration. But it does so by removing you from time, by suspending your participation in the flow of events, by turning you into a passive object rather than an experiencing subject. You sleep through the journey. You experience nothing. You are, functionally, dead for the duration, awaiting resurrection at the destination. And here is the key point. If you are going to sleep through the journey anyway, if you are going to remove yourself from conscious experience, then why not use relativistic speeds? Relativistic time dilation allows you to cross vast distances while experiencing relatively little proper time, and you remain conscious during that time. You can live, work, think, experience the journey. You are not suspended. You are active, engaged, alive in the fullest sense. The hibernation fallacy is the belief that you can avoid the costs of time dilation by simply sleeping through the journey. But you cannot. The costs are not biological, they are temporal. The separation from your era is not caused by your aging but by Earth's aging. And Earth's aging is determined by the velocity of your spacecraft, not by the state of your metabolism. This is a difficult concept to internalize because we are accustomed to thinking of time as experienced subjectively. We think of time passing as something we feel, something we endure. When we sleep, we feel like no time has passed. We close our eyes and open them, and it feels instantaneous, even if hours have elapsed. So it is intuitive to think that hibernation skips time, that you can avoid the passage of time by not experiencing it. But time does not care about your experience. Time passes whether you are conscious or unconscious, awake or asleep, alive or dead. And in relativity, the rate at which time passes depends on your velocity, not your metabolic state. You cannot slow time by slowing your metabolism. You can only slow time by moving faster. There is one narrow scenario where hibernation is genuinely useful: generation ships traveling at sub-relativistic speeds. If your spacecraft cannot achieve significant time dilation, if you are limited to, say, 10% light speed, then journeys to distant stars will take decades or centuries of proper time. The original crew will die en route. New generations will be born, live their entire lives aboard the ship, and die without ever seeing the destination. The journey becomes multi-generational by necessity. Hibernation offers an alternative: put the crew in suspension, launch the ship, and wake them upon arrival. The journey still takes decades or centuries of proper time, but the crew experiences only the brief moments of wakefulness at the beginning and end. They skip the journey, avoiding the need for a self-sustaining population, avoiding the social and psychological challenges of generation ships. In this specific case, slow speeds, long journeys, hibernation is a valuable technology. But it is not a substitute for relativistic speeds. It is a workaround for the limitations of slow travel. If you have relativistic speeds, hibernation becomes largely unnecessary. A journey that takes 50 years at 10% light speed takes 5 years at 90% light speed, proper time, and the crew can remain awake for the entire 5 years, experiencing the journey, maintaining the ship, conducting research. No hibernation required. The hibernation fallacy persists because it appeals to our desire for a loophole, a way to avoid the costs of relativistic travel without actually traveling relativistically. We want to believe that we can sleep through the temporal separation, that we can wake up in the future without having paid the price in time. But physics does not provide this loophole. The only way to reduce the time elapsed in your reference frame is to move faster. The only way to compress the journey temporally is to approach light speed. And when you do that, hibernation becomes redundant. You are already experiencing minimal proper time, already skipping decades or centuries of Earth time while aging only years. So the hibernation fallacy is not just a misunderstanding of physics, it is a symptom of denial, a refusal to accept the fundamental reality of time dilation. We want there to be an easier way, a less painful solution, a method that does not require us to confront the full implications of temporal exile. We want to believe that we can have our relativistic journey and return home to find everything unchanged, as if we had simply been asleep. But we cannot. The universe does not permit it. Time dilation is real, hibernation is irrelevant, and the only choice is between traveling slowly and experiencing the full duration of the journey, or traveling quickly and accepting the temporal separation that velocity imposes. There is no escape. There is no loophole. There is only the ladder, and the price we pay to climb it. If relativistic travel is too costly, too technologically challenging, too emotionally devastating, then perhaps the solution is to abandon speed entirely. Perhaps we should accept the vast distances between stars and the centuries required to cross them. Perhaps we should build not spacecraft but worlds, vessels large enough to sustain entire populations, where generations are born, live, and die during the journey, where the destination is not a place one person reaches but a promise inherited across centuries. These are generation ships, sometimes called world ships or arc ships, and they represent a fundamentally different philosophy of interstellar travel. Where relativistic missions attempt to compress the journey temporally through speed, generation ships stretch the journey socially through population. Where relativistic travelers experience years while Earth experiences centuries, generation ship inhabitants experience centuries while Earth experiences centuries. The temporal asymmetry disappears. Everyone ages together, just separated by space rather than time. The engineering of a generation ship is daunting but conceptually straightforward. You need a vessel large enough to support a self-sustaining ecosystem, agriculture for food, recycling systems for water and air, habitats for thousands or tens of thousands of people, industrial facilities for manufacturing and repair. You need genetic diversity to avoid inbreeding over multiple generations, at minimum, several thousand initial colonists, with careful genetic management to maintain a healthy population. You need social structures that can endure centuries without external contact, governments, laws, education systems, cultural traditions, methods for resolving conflicts and maintaining cohesion across generations who will never see Earth or the destination. And you need to address a fundamental psychological question: How do you motivate people to undertake a journey they will not complete? How do you convince the original crew to board a ship knowing they will die en route, that their children will die en route, that perhaps their great-great-grandchildren will be the ones to finally reach the destination? How do you maintain purpose and morale across centuries when the goal is abstract, theoretical, visible only as a point of light growing slowly brighter over lifetimes? Generation ships do not benefit from time dilation because they travel too slowly. If your maximum velocity is 10% of light speed, achievable with nuclear pulse propulsion or other non-relativistic technologies, then the Lorentz factor is only 1.005. Time dilation is negligible. A journey to a star 100 light-years away takes 1,000 years Earth time and 995 years ship time. The difference is 5 years over a millennium, irrelevant on the scale of the mission. So the generation ship inhabitants experience the full duration of the journey. They live their entire lives aboard the vessel. Children are born who have never seen a planet, never experienced weather or natural gravity or an open sky. They grow up in corridors and chambers, their world measured in decks and modules, their entire existence contained within the metal walls of the ship. They are told stories of Earth, of oceans and mountains and forests, but these are myths to them, legends from a distant past, as abstract as heaven to the faithful. And they are told about the destination, the new world they are traveling toward, the planet they will colonize, the future they are building. But this too is abstract. The star is a point of light, indistinguishable from thousands of other points. The planet is an invisible speck, its existence inferred from spectroscopic data collected before departure. It may have oceans. It may have an atmosphere. It may be habitable. Or it may not. The information is decades or centuries old, transmitted at light speed from probes sent ahead or from observations made before departure. By the time the ship arrives, conditions may have changed. The planet may be uninhabitable. The journey may have been for nothing. This uncertainty is a defining feature of generation ships. Unlike relativistic missions, where the crew experiences the journey and can assess conditions upon arrival, generation ships commit multiple generations to a destination chosen by their ancestors, based on data that may be obsolete by arrival. The inhabitants live and die in service of a goal they did not choose, toward a world they have never seen, on faith that their ancestors made the right decision. The social dynamics of such a mission are fascinating and terrifying. Studies of isolated communities suggest that populations need careful management to avoid social collapse. Without external threats or opportunities, internal conflicts can escalate. Power structures can become rigid or tyrannical. Cultural stagnation can set in. The ship becomes not a vessel but a world unto itself, and like any world, it is subject to all the pathologies that afflict human societies: inequality, oppression, violence, corruption. Some generation ship designs attempt to mitigate these risks through social engineering. Implement democratic governance with checks and balances. Foster cultural traditions that emphasize the mission's importance. Provide education that instills a sense of purpose and continuity. Create art, music, literature that celebrates the journey and connects inhabitants to their heritage. Use virtual reality to simulate Earth environments, giving inhabitants experiences of nature and open spaces. Rotate leadership to prevent entrenched power structures. Encourage genetic and cultural diversity to maintain adaptability. But these are fragile interventions, easily disrupted by unforeseen events. A crop failure could trigger famine and resource wars. A charismatic leader could establish a dictatorship. A religious movement could reinterpret the mission as divine pilgrimage, rejecting scientific management in favor of faith-based governance. A generation could simply lose faith in the mission, concluding that the destination is impossible or undesirable, and mutiny, demanding the ship return to Earth or divert to a closer star. And here is the darkest possibility: the journey could succeed technologically but fail socially. The ship could reach its destination in perfect working order, systems functioning flawlessly, only to find that the inhabitants have forgotten the mission. That over centuries, the knowledge and purpose that motivated departure have been lost, replaced by new myths, new priorities, new identities that have nothing to do with colonization. The inhabitants might not even recognize the destination star as significant, might sail past it, continuing into deep space, the mission forgotten, the species aboard the ship evolving into something new, cut off from humanity, becoming post-human not through technology but through isolation. This has happened before in human history. The Polynesians who settled remote Pacific islands sometimes forgot their origins, lost the navigational knowledge that brought them there, developed new mythologies that explained their presence without reference to migration. If this can happen across a few generations on isolated islands, what happens across hundreds of generations aboard a ship in the void? Generation ships also face a strategic vulnerability that relativistic missions do not: obsolescence. If a generation ship departs at 10% light speed for a destination 100 light-years away, it will arrive in 1,000 years. But propulsion technology improves. 30 years after the generation ship launches, humanity develops fusion drives that enable 50% light speed. A new ship launches, traveling 5 times faster, and arrives 800 years before the generation ship. When the generation ship finally arrives, it finds the star system already colonized, already developed, already inhabited by descendants of Earth who took a faster route. The generation ship crew, who sacrificed centuries in service of colonization, arrive to find themselves redundant, their sacrifice wasted, their purpose fulfilled by others who did not bear the same burden. This is the weight equation problem, formalized by mathematician Andrew Kennedy. If technology is improving, is it ever the right time to launch an interstellar mission? Or should you always wait for better technology, faster propulsion, higher success probability? The generation ship, with its centuries-long journey, is especially vulnerable to this problem. By the time it arrives, it may be an antique, a relic, a historical curiosity rather than a pioneering mission. And yet, generation ships have one profound advantage over relativistic missions: they do not impose temporal exile. The inhabitants age together. Families remain intact across generations. Social bonds are not severed by time dilation. When the ship reaches its destination, the inhabitants step out into a universe that has aged at the same rate they have. There is no returning to find Earth unrecognizable. There is no loss of loved ones to differential aging. The social fabric, though stretched across centuries and confined to the ship, remains continuous. This makes generation ships psychologically easier in some ways. The inhabitants are not exiles from their era, they are pioneers in real time, moving through space at a pace that keeps them synchronized with the rest of humanity. They can receive updates from Earth, though time-delayed by light-speed communication. They can follow human history as it unfolds, watching civilizations rise and fall, technologies advance, cultures evolve. They remain part of the human story, even if they are physically distant. But they pay a different price. They experience the full duration of the journey. They live centuries in transit, perhaps dozens of generations, before reaching the destination. Their entire civilization exists aboard the ship, and for most inhabitants, the destination is not a personal goal but an inherited obligation, a promise made by ancestors long dead. So the choice between generation ships and relativistic ships is a choice between two kinds of sacrifice. Generation ships sacrifice speed for social continuity. Relativistic ships sacrifice social continuity for speed. Generation ships take centuries and keep everyone aging together. Relativistic ships take years but separate travelers from their era. Neither is easy. Neither is painless. Both demand that we choose what we value more: staying connected to our timeline or reaching the destination within a human-scale duration. The universe offers no compromise. And so we must decide: do we build slow ships that preserve social bonds but require generations of sacrifice? Or do we build fast ships that compress the journey but sever temporal connections? Do we accept centuries of life in transit, or do we accept becoming strangers to our own species? The generation ship alternative is not a solution. It is a different formulation of the same problem. The stars are far. The journey is long. And whether we measure that journey in subjective years or objective centuries, the cost remains profound, inescapable, written into the geometry of spacetime itself.